Hello and welcome to Chapter 11, Acids and Bases. Acids and bases are actually very common substances that you might encounter in many places in your day-to-day life. For instance, this picture illustrates a glass of soda which contains phosphoric acid, H3PO4, and carbonic acid, H2CO3. Acids and bases have been known for a long time, at least since ancient Greece. The word acid is actually from a Greek root meaning sharp or sour, and comes through the Latin word acidum, meaning sour wine, or more specifically vinegar, since that's what you get when you let wine ferment for too long and turn sour. We sometimes use the words alkali or alkaline to refer to a basic substance or solution. This comes from the Arabic word kala, meaning to roast, and alkali, meaning the roasted ashes, which refers to the original process of heating plant ashes and extracting them with water to create what we now understand to be a basic solution. So in this first section, we're going to learn some of the properties and descriptions of acids and bases, as well as how to name them. Given this long history, it's no surprise that scientists have come up with many different theories over the years to explain the properties of acids and bases. Most of these theories turned out to be seriously mistaken in one way or another, up until about the late 1800s when a physical chemist named Svante Arrhenius put forward his ideas. Arrhenius proposed that acids were substances that increase the concentration of hydrogen ions in aqueous or water solutions. To put that another way, acids are substances that dissociate in solution to produce hydrogen ions, H+. In fact, Arrhenius was best known for his work on electrolytes, which he won a Nobel Prize for in 1903. And this definition of acids shows that they're really a special kind of electrolyte. So this is the first modern chemical explanation of how acids work, but as I said, it's been known for a long time that acids have a characteristic sour taste, they can turn litmus paper red, and they can corrode or dissolve some metals. We'll begin by looking at the naming conventions for acids. It's important to keep in mind that acids don't really fit neatly into the ionic versus covalent categories that we've been dealing with until now. Part of the reason for this is that hydrogen itself is somewhat unusual. We consider it a nonmetal and it forms many covalent compounds, but it's also able to form positive ions the way that a metal would. So for this reason, the naming of acids doesn't fit with the naming conventions for either type of compound that we've learned until now. There are actually two broad categories of acids that have slightly different naming conventions. The first type of acid that we're going to deal with is sometimes called a binary acid because it's formed from hydrogen and one other element. It's formed from a hydrogen ion, H+, and some other nonmetal. These acids are named with a prefix of hydro, and they end with ic acid. So for instance, the name of the acid formed from chlorine, or the chloride ion, is hydrochloric acid. The other type of acid are ones that contain a hydrogen ion and a polyatomic ion. Since these polyatomic ions are usually oxygen containing, these are also called oxoacids sometimes. So these acids are named by taking the name of the polyatomic ion and changing the ending depending on what it is. So if the polyatomic ion ends in ATE, then the ending gets changed to ic acid. If the polyatomic ion is ITE, then it gets changed to us acid. So for instance, ClO3- is the chlorate ion. If you were to bind ClO3- with one H+ ion to create the neutral compound HClO3, this would then be known as chloric acid. ClO2- is chlorite. It's similar to ClO3-, but it has one less oxygen, and so the ending has an ITE. So if you take ClO2- chlorite and you combine that with hydrogen, you create the compound chlorus acid. This chart shows the names and formulas of some of the most common acids that we'll encounter in this class. It also shows the names and formulas for the counterion or anion present. Remember, every acid can be seen as a hydrogen ion bonded to some other negative ion or anion. In this case, the first four rows here, from fluoride, chloride, bromide, and iodide, are all the monatomic ions. These are all individual single atoms with a negative charge, and so these form what I was referring to as the binary acids: hydrofluoric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Further down in the chart, we have the oxygen-containing polyatomic ions, so things like nitrate, NO3-, nitrite, NO2-, carbonate, CO3 2-, and these form what are referred to as the oxoacids. And the naming here depends on the name of the ion. So any ion that ends in ATE, nitrate, sulfate, carbonate, acetate, phosphate, these all form acids that end in ic acid. So nitrate becomes nitric acid, sulfate becomes sulfuric acid, carbonate, carbonic acid, phosphate, phosphoric acid, acetate, acetic acid, and so on. Those that end in ITE form us acids. So nitrite is nitrous acid, sulfite is sulfurous acid, phosphite is phosphorus acid. One that I left out, you can see in the middle here, is hydrocyanic acid. That's because this is formed from a polyatomic ion, but it's not oxygen containing, and so the name actually fits more with the binary acid nomenclature. So even the ion is named cyanide, it ends in IDE rather than ATE or ITE, and so from the IDE ending, it gets named as if it were a binary acid, hydrocyanic acid. That's an exception to the rules, a little hard to remember, but it's not one that's encountered very frequently. So for now, matching up the formula of an acid to the name may just be a matter of referring to that table. Over time, you'll get used to it, you'll start to see the patterns in how the names of the ions relate to the names of the acids, and it'll become easier. Of course, this will also be easier if you've already remembered most of the table of polyatomic ions. So HBr, we know, is a binary acid because it's just hydrogen ions, H+, and bromide ions, Br-. So this is going to have the name of a binary acid, which will always begin with hydro. So just from that alone, we can see that C is the correct answer. Hydrobromic acid comes from the bromide ion. In the second example, we have H2CO3. In this case, you actually have two hydrogens. We'll discuss what that means a little bit later. And the negative ion in this case is CO3 2-. So this is an oxoacid, which means it's not going to begin with hydro, and we can say that B is not the correct answer. But in order to choose between A and C, we have to know the name of this ion, this CO3 2-. Well, this CO3 2- is called the carbonate ion, and so the ATE ending becomes ic acid. So A is the correct answer. Carbonate forms carbonic acid. The last example is HBrO2. Here you again only have one hydrogen and then the BrO2 ion, which is going to have a -1 charge. This is again not a binary acid, so B can't be the right answer. But we have to know what BrO2- is. And BrO2- is bromite. It ends in ITE, and so this acid is bromous acid. Of course, in studying acids, it's also natural to study bases as well. And so Arrhenius proposed that bases were a kind of substance that would produce hydroxide ions in water. The hydroxide ion is the OH- ion. That's an important one that you should have remembered from your table of polyatomic ions. So a substance like sodium hydroxide, NaOH, is a base because it dissociates in water and it produces sodium ions, but more importantly, it produces hydroxide ions. These are also obviously electrolytes because we have a substance dissociating into ions in water. These have a bitter or chalky taste, although in most cases, foods and things that we consume are not typically bases. They also turn litmus paper blue, as well as turning phenolphthalein, which is a special indicator, pink, where it's normally clear in acidic solution. Bases also feel soapy or slippery to the touch, and in fact, bases are substances that are used in the production of a lot of different kinds of soap, and have been for a long time historically. The naming system for bases is much easier because almost all of the bases that we encounter are really ionic compounds containing the hydroxide ion, and so they're named just as a typical ionic compound would be named. So NaOH is just sodium hydroxide because it's a sodium ion and a hydroxide ion. KOH is potassium hydroxide. BaOH2 is barium hydroxide, AlOH3 is aluminum hydroxide. Remember, these are like ionic compounds, so we don't need to use any prefix or anything to indicate how many hydroxides or how many positive ions we have. The charge balance can tell us that. In some cases, we will have transition metals hydroxides, which means that we'll need to include the Roman numeral to specify the charge. But again, the rules there are really no different from what we learned for ionic compounds already. This chart summarizes these characteristics and properties that we've talked about already. The most important being that the acids produce hydrogen ions, bases produce hydroxide ions, and they are both electrolytes that produce ions in solution. So now we're going to try and name some acids and bases from the formula. The first thing that we need to do is figure out from the formula whether a substance is an acid or a base. Now, typically acids will begin with an H. They'll have a hydrogen right up front, and that hydrogen is the one that breaks apart and forms an H+ ion in solution. So for a formula like HNO2, it should be relatively clear that this is an acid, not a base. It also should be clear that this is an oxoacid, meaning an acid containing an oxygen-based polyatomic ion, and so we really need to know the name of this ion, this NO2. So this NO2- ion is actually called nitrite, which makes this nitrous acid, D. The second one here, CaOH2, doesn't start with an H. Obviously, it actually has OH ions in it, so this makes it a base, a hydroxide-containing compound. In this case, we have Ca, which is calcium, and 2 hydroxides. There's no need for any Roman numeral or any prefixes or anything like this. This is simply E, calcium hydroxide. The third example is H2SO4. Here we have, again, hydrogens at the beginning, and then a polyatomic ion at the end, SO4. This is the ion SO42-, which is actually called sulfate. And so this is sulfuric acid, B. Notice that the ATE ending doesn't always just get dropped for ic acid. Sometimes another syllable is included, generally just for the purpose of making the name sound a little more fluent, right? So sulfic acid doesn't have quite the same ring to it that sulfuric acid is. So there are certain things like that that you need to look out for, but they should become clear as you deal with these things. The next example is HiO3. This is an I, not an L, so be careful about that. And this is IO3-, this ion, which is actually the iodate ion. And so ATE ending becomes ic acid, so this becomes iodic acid, A. And then obviously by the process of elimination, the last one is C, but it should be pretty clear that Na is sodium and OH is hydroxide, so this is sodium hydroxide.